Good morning. So we were now going to start in our vehicle dynamics course an important part of vehicle dynamics that's called lateral dynamics, otherwise called vehicle handling dynamics. Right. So just to have where are we in our course to have our mapping ourselves and learning the content of the course. Let's look at the various modules in the syllabus copy and what we were done and what all left to do and how are we going to organize our forthcoming lectures, including today's class. So with that, I'm going to start today's class. So see module 1 and 2, we have already completed. Module 1, we have learned basics, fundamentals of mechanical vibration. And module 2, we are able to apply that for vehicular vibrational study. That's otherwise called the vertical dynamics part of vehicle dynamics, called the ride dynamics, ride and comfort dynamics study. So that we have done nicely, importantly, having 4 folds of that part. Looking at mathematical models, essentially 2 nice models, quarter car model and pitch and bounce model we have seen for harmonic excitation. And secondly, we looked at the road characterization because the road undulation is primarily acting as an input for this vibration model for ride dynamics. So how can you characterize your road and represent that as a random function and ultimately get an input to the model as a power spectral density function from the road surface, and that act on a vehicle characteristics called a vehicle transfer function and gives you vehicle target response in a power spectral density form. So if we have that power spectral density function, you would be able to integrate it over a band of frequency you have interest and to get your RMS acceleration. So this is essentially what you have learned in the second fold of ride dynamics. In third fold of ride dynamics, we were looking at importantly, what are this human perception for this vehicular vibration? How are they quantified in a real-time scenario and in industrial practice, such as subjective evaluation procedure or in-lab component test or ride simulators are really going to take a vehicle on the test track, road experiments are conducted to get your vibrational noise response in your vehicle to assess quantitatively the acceleration and noise levels that would be correlated with the subjective rating provided by juries, well-trained juries and their commands. So that helps in a loop product development as a whole. So this is what in a third fold we have seen. Essentially, we looked at 2 important standards, SAE Janeway's standard for frequency band of 0 to 60 hertz, and then again 1 to 60 hertz and 1 to 80 hertz whole body vibration of any vibration environment of human perception. For that matter, in a vehicle, whole body vibration is given by ISO 2631 standard under safety region, proficiency region, and advanced region. So there are 3 bands in that, and there are ratings for XYZ direction perception and so on. So these standards and this kind of general awareness we have got, and that to do that was an objective of ride dynamics to improve your comfort in your vehicle. You should essentially good at 2 other folds: understand the input, that is road nature, and understand the response, that is in a vehicle, through mathematical modeling. So in that process, again, we have fine-tuned ourselves and focused study of suspension role for ride dynamics, where it has to fulfill to see that the energy from the road doesn't enter to the vehicle body, that's sprung mass, so that it is acting as a good isolator in a vehicle. And you also have seen that is not only the function of suspension, also the suspension should have necessary travel of your unsprung mass, so that the travel space called the lateral space requirement, and importantly the road grip of your tire by tire dynamic deflection, that's called the road holding of your vehicle. So these all 3 aspects to be met by suspension, and we understood that suspension by passive nature is difficult. That's where the role of active or semi-active suspension system do come into picture. So, of course, this is part of 4th fold of ride dynamics mentioned in your syllabus is the contemporary issues, which are an upcoming advancement in suspension modules, which are going to be more intelligent, not only to take care of human operated vehicle for its requirement of all three dynamics aspects, performance or handling or ride, also to map with a version of powertrains that come in your vehicle, like a hybrid vehicle or e-mobility vehicle, or for that matter, the tomorrow's era is going to be in most of the places in the developed countries, and you see an autonomous vehicle study. So when it is an autonomous vehicle study, what is the role of suspension for that? All to understand, we have to have this contemporary issue. That's why those two topics were mentioned in module 8. So this is all we have studied. So module 1, 2, and 8, we have just made a coverage before CAT 1 and quite a good learning in that part. And then now we are going to get into another important part of dynamics called handling dynamics, otherwise called lateral dynamics. So in the syllabus, this lateral dynamics has been spread across module 7, module 5, and module 6, titled as vehicle handling, cornering behavior, suspension, and roll stability. And then module 3 again, stability of vehicle, and so on. So the syllabus content primarily had a main objective of primarily on a ride and handling side. And then you had a module 4, tire dynamics and vehicle performance. That is together as for a longitudinal dynamics. So this is what is the content of your syllabus. So this rest of these 5 modules, I'm going to organize in a way that we'll start with module 7, vehicle handling. We'll understand what are the necessary governing equation to do this lateral dynamics aspects. And then we will get into slowly the stability analysis of the vehicle and so on. So that is how we are going to study module 7, 5, 6 in a whole, and roll off suspension in your stability part. That's called rollover stability or roll dynamics part also in specific we are going to study. So then we will be the last part of our dynamics, where we will focus more on performance and the roll of tire for the performance. That's tire dynamics, how the tractive or braking effort are developed, the tire road interaction and so on. So this is all something that we are going to study further, and so that we will have a wholesome fundamentals of this important course vehicle dynamics, right? So summarizing and orienting ourselves nicely like this, I think we would be confidently having march ahead of learning further for this CAT 2 examination upcoming in October last week also. So what am I going to do in this particular period is I'm going to teach you a general framework wherein you are going to look at how are you going to develop the necessary governing equation in order to take care of lateral dynamic aspects. So when I say that, what is the difference between lateral dynamics and vertical dynamics? In vertical dynamics, we have studied mostly of vibrational model. Where that study is to know what is the target response levels and so on. Whereas in lateral dynamic study, it is more of characteristic study of your vehicle. What I mean by characteristic study of your vehicle is my vehicle is responding to my need. So as a driver, if I drive my vehicle, am I able to ride my vehicle the way I want? So when I have vision and look at the ahead of a turn, if I do an input giving a steering, is my vehicle listening to me and going in the course nicely or not, without any problem? And that is what is something called handling characteristics or characteristic of vehicle. So this study is mostly of characteristic nature of vehicle, which is going to constitute two important objectives. One is the control of your vehicle, directional control of your vehicle. Another one is directional stability of your vehicle. So these are the two folds of your lateral dynamics that we are going to study. And in a simplified way, from the point what you know to explain what is lateral dynamics is what is 2D and 3D motion of your vehicle, right? So what do you mean by 2D motion of your passenger car? You don't go in straight motion. So when you drive in a straight motion, it is more concerned with the only tractive force and braking action in line, and 1D motion. where that is primarily required other than your steering input. So you are going to hold steering as such in a condition where vehicle to be driven only in a straight path. That is 1D motion, where the vehicle nature or its motion all primarily governed by equation in a longitudinal direction, and that's what is fall under the category of longitudinal dynamics. We are going to study that separately after this lateral dynamics. The moment I see my road is not straight, I do have to take a turn. I do an input to my vehicle, what is called a steering input. So I do a steering of the vehicle and give the steering input. So that is what is going to bring in the significance of dynamics part called lateral dynamics or vehicle handling dynamics part. So that is how we can short to say and understand what is this handling dynamics. So if we go more in detail, know or define what are this handling dynamics, the responsiveness of a vehicle for the driver input, that is particularly a steering input, is what is called handling dynamics. So ease of control is there exist in your vehicle. So I go straight and I steer, I'm able to control my vehicle on my covered path. So that is what is called responsiveness of your vehicle, if that is met for the given steering input, and that's what is called handling dynamics. And we can also say this handling is an overall performance measure of vehicle driver combination in the vehicle. So vehicle and driver combination. Why? Because the input is right dynamics, not a input that comes from the driver, that comes from the road surface undulation. Now for the vehicle, the input comes from the driver straight away explicitly by steering input. So the driver vehicle combination study, what is called handling. You would see such kind of statements as well in a standard textbooks and literature. And you would also see still slightly go in detail of looking at the control system aspect, the stability system aspect. When I say 3D motion of a ground vehicle, what do you mean by that? The vehicle has to go in a ground plane, that is 2D motion always. A 3D motion is something talking about its unstable state. When a vehicle is rolling over, no, it's going out of the contact of tire with the road contact. And that is what is called a 3D motion of a passenger car. So we never want a 3D motion of a passenger car unless we see that to enjoy in a movies safely. They do take care of that. We don't require a 3D motion of passenger car on the road surface, right? We wanted to do only the 2D motion. So our vehicle dynamics become how nicely simplified. So 1D motion and 2D motion alone. So we don't bother about 3D motion unless and until I'm going to get an idea of looking at the stability part of my vehicle and how can I ensure always stable motion of a vehicle, that's 2D motion. All then we will mathematically look at the condition of rollover stability, and that part of dynamics would be 3D part. We will also have lectures for that part in our study. And the control aspect, when I talk, it is the closed loop system. What I mean by closed loop system, see, I've been driving my vehicle in a highway. I know there is an ahead truck going, which is slower than my speed on the highway. So I have to overtake. So what I do, I will go straight in this path. This is a truck going and this is my vehicle. So I go just and take a overturn, not overturn, no, take a overtaking on one side and then go ahead. So that's called a double lane change. So I go in a lane and then change my lane and then overtake the ahead vehicle and then go again in the earlier lane. And that is what is called closed loop test, called a double lane test. So your vehicle has to respond like that. I have my vehicle, I have to change my lane and come back to my lane. If my vehicle is responding to that, and that vehicle is a good handling vehicle. Why it is required? Because that situation would be more when you drive on a highways, right? You have to overtake vehicles. So essentially your vehicle to do that task. And why is it called a closed loop? Why? Because you give an input, steering, and then you know what is that your vehicle to take a path, and then your vehicle is responding. Accordingly, you are correcting your steering, and then you are going. So when you give an input and you see what's happening to the vehicle, and then again you correct your steering, and then you go. That means there is an interaction between vehicle, environment, and driver. So this is kind of a closed loop system. So the double lane test, if you look at in literature, a textbook, that's called a closed loop test. Then you may ask now, is there anything called the open loop test? Of course. So why is it required? That open loop test is required for the purpose of characterizing your vehicle and saying handling behavior, directional behavior of a vehicle. What are such tests? So take your vehicle on a highway where there are no other vehicles are not there. So you are a test engineer, you have your test track where your vehicle alone there, and your road vehicle surface is very wider road, and you go straight and give an input called pulse steer. What do you mean by pulse steer? Pulse means it's an impulsive force. You give a shortest duration force, that's an impulsive force. You give a shortest duration moment, that's an impulsive moment. So that's kind of input that you're giving to your vehicle. So I go straight, drive my vehicle straight. Suddenly I'll give a steering pulse and take back my vehicle. So that is not a closed loop. That is giving a pulse input to the vehicle, and you see what's happening to your vehicle, right? You give a ramp input. So you go straight and suddenly give a steering, and your vehicle goes in what direction you look at. So those are just you give an input and see what is happening, and you are not correcting anything. And that is what is called an open loop test. And that is essentially conducted for the behavior of vehicle. That's called a directional behavior prediction test. So such kind of tests are there common in vehicle handling dynamics. And an important definition called an understeer gradient. That is what is called a measure of vehicle handling nature. And that understeer gradient is normally described for a steady state motion. Of course, there are transient effect on this understeer gradient because of different design aspects and operating condition of a vehicle that also we are going to study. So importantly, we will be having hopping around or taking in hand an important aspect called understeer gradient, and we look at an entire lateral dynamics study. So this understeer gradient, how does it come in our study? Is that through any equation? Yes, that's the governing equation of your vehicle model called the bicycle model, and the simplest, easiest model of your vehicle, but a popular and very good model to study your vehicle handling. That is directional response and stability analysis. So this is all what is the crux of your lateral dynamics, and terms and terminologies. Suppose you are asked, you are supposed to clearly state and answer the way I have been explained for a few minutes now. So now, what is my objective for another 40 minutes also in this lecture? Is to take you to a mathematical world, and then that's a simple world. People feel that's complex, but you will feel that simple at the end of the lecture. And that equation is what is called a Newton-Euler equation for a rigid body in space. I'm going to explain you that. And that's what is the agenda and objective of this particular period. So now let me just share my board and start lecturing. Are you getting the sense of what are that we are going to do? You have any doubts, you can ask at this moment. Otherwise, we will go ahead at the end, you can put your doubts. All right, so this is lecture number 18, and today's date is 24/09/2021. And we are in handling dynamics. What do you mean by that? It is lateral dynamics is part of vehicle dynamics. So this is what we are going to study, and today's class we are going to look at a general framework. We are going to revisit our mechanics, what you have learned in this class, and we are going to take that to a level, advanced level, wherein you are able to model your vehicle even for a hybrid vehicle. What I mean by hybrid vehicle, it is not a powered vehicle with IC engine and electric plane I'm talking about. The hybrid vehicle is what was an yesterday's vehicle that was popularly came and got on everyone's attention in India Today magazine. That is what is called a hybrid vehicle, which is a flying car. The startup in Chennai, they have come up with an idea of developing a vehicle, first vehicle in Asia which could run on road and fly on sky. So it's called a hybrid vehicle now, right? And that vehicle, CEO Yogesh Iyer was stating that it is from the concept of the bird fly. So they put some name, specific name for that, and it was a very catchy news yesterday, and it was viral share among social medias. So I thought that is the right time when I teach these courses come, and that would nicely fit in today's lecture. So I just give that example. That's the reason. So when you have to look at such kind of vehicle and its dynamics, what today you are learning is what is the fundamentals that has to be obeyed and implemented in such a kind of startup vehicle. Confidently, you should say that. That's what at the end of the lecture you will appreciate with this particular class, right? So what I mean by general frame of work here is you are going to be familiar with these three aspects at the end of the lecture. One is you will know what is clearly inertial. What is clearly inertial frame of reference. And you'll know clearly what is body fixed coordinate system. And you would be able to derive an important equation for motion of rigid body in space that's called the Newton-Euler equation. So these are the three aspects at the end of the lecture you will be clearly knowing equations. So I would start this lecture from the point well known to you, which is curvilinear motion in your rigid body mechanics that you have studied with a particle ideology. When I say curvilinear motion, it is particle kinematics. So what do you mean by particle kinematics? Particle means it is a rigid body only, but you do not look at the physical geometry of the rigid body. You only account its weight of the body, and other forces all are not considered as it is kinematics. Your vehicle physical geometry is neglected, and you look at its motion geometry alone is what is called kinematics, and that part is called particle kinematics. You know that we were understood with this coordinate system, say x, y, and I have here my curved path, and I would be able to represent the motion of my vehicle now here. I represent it by a particle now. Instead of the physical geometry of my vehicle, this is my car now on this path, it goes in this. So I would be able to explain my motion geometry by its position vector R, and I would be able to explain my motion of this in this path, its trajectory, by its velocity, always tangential to the curved path, velocity vector. And I would be able to explain my acceleration, what rate this velocity changes, and how nicely it is having its direction control on the path to say its acceleration vector. You know that always it fall on the curvature side. When it goes in this side, the acceleration vector will be on that side. So if it is decelerating, slowing down, this acceleration vector on this other way. So you studied this well in your rigid body mechanics. So you would have two components of this. One is tangential and is normal component. Tangential component responsible for change in magnitude of velocity. Normal components for the holding of the vehicle on the curve and so on. So the lateral or the normal acceleration is what is primarily for your handling dynamics. That is to have a directional control. That's what this I was talking about in this. So one is what? Directional control. Another one is directional stability. So these are the two primary objectives of lateral dynamics of a vehicle we are going to study, right? So the directional control comes from where? Comes from this part of the component A y or a n here, normal component with respect to this path. With respect to vehicle, it is lateral direction, ay we call it, right? But I don't consider now geometry, so time being, we just look at, and this is responsible for directional control of your velocity. And this component here, when you project and you get, is what is at, that is tangential component along the direction of velocity, in the line with the velocity. So if this is positive, this would increase. If it's negative, this would decrease. So this is what something that we have learned. And this is not sufficient now, right? With that, I cannot just to say my stability analysis or even direction control, I have to give an input all in a vehicle dynamics perspective when I study. This is not sufficient, but of course, this particle kinematics is quite sufficient if I am only interested in at any point of time what is the position, velocity, acceleration, and the path of my vehicle as an observer from this fixed frame of reference called an inertial frame of reference. So this xy is fixed where? It is fixed in the ground, in the surface of Earth. So the axis system, Cartesian coordinate system, which is fixed on the ground, is what is called an inertial frame of reference, where your Newton's law holds good, your Euler equation holds good. Of course, you may ask and wonder the question, is that Earth surface, Earth is rotating. How can you say that your inertial frame is correct? Inertial frame means what? It is non-accelerated frame, non-rotating frame. That's what is called an inertial frame. So when I make that statement, there's a doubt, Earth is rotating about its own axis and rotating, going around an elliptical path around the sun. So how can you say that? We can say that it's an approximation and valid because any vehicle motion on the Earth surface, that acceleration what we look at here in this involved with the vehicle are much higher than that of the acceleration of your Earth and the surface velocity of your Earth. So the valid assumption is goes good. So other than the axis fixed on the Earth, if you have to consider in your dynamic study to account dynamic quantities, and you say that is an inertial frame of reference, that frame should not have acceleration and should not rotate, right? So that is what is called an inertial frame of reference. You shouldn't have any doubts. If we have a dynamics and inertial frame of reference that obeys Newton's Euler equation, that's first thing. And what is this body fixed coordinate system? So body fixed coordinate system is very much important. The moment I come out of this particle kinematics and come to rigid body ideology, rigid body dynamics, particularly kinematics part, without considering cause of the motion, I require the vehicle geometry, and my system of axis is no more, no, only two I will consider. Also, I will have to consider the third axis. So for 2D motion, I consider my XY plane as the top view of my plane, and the ground plane I consider. Whereas in three-dimensional study or vehicle which is in space for the flying car study, what is essentially required is an inertial frame, Cartesian coordinate system fixed in the ground, which is in 3 dimension. So that axis system is what is this? Let me represent that as capital X, capital Y, and capital Z, which is now inertial frame of reference in the ground fixed coordinate, right? So now I have my vehicle in space. For that matter, let me consider my vehicle, which is an aircraft. So this is an aircraft that I consider. So this aircraft flying now would have an axis fixed in its CG location. Say that is this is the CG location, and I have a coordinate system here. The forward direction is X, and lateral direction is Y, and the downward direction is Z. And these are represented by unit vector I, J, K. Right? And this is what is called the body fixed coordinate system. So why do I have to consider body fixed coordinate system? What is the advantage of this? If I consider this aircraft as a particle in 3D, and I can give always the position of that its path from inertial frame of reference. But to understand the velocity and acceleration variation with respect to body coordinate system is important. Maybe it is not possible to give a position of body with respect to body fixed coordinate system. So in such cases, we have equations is going to be bit appearing complex, and we are going to look at that in today's class. So first, you please understand that axis fixed in this aircraft at CG location is for to have its 6 degrees of freedom. How many degrees of freedom body in space do have? It can have 3 translation in this 3 direction. Aircraft can thrust ahead, and an aircraft can descend or ascend in vertical direction. Aircraft can have a lateral thrust, lateral motion, or when it takes a turn navigating, then there will be this motion. So this all translatory motion, as well as the aircraft can roll about this axis. So that's given by roll rate P. What is this called? A roll rate. So rotation of this is roll motion. With respect to time, its variation roll rate in x-axis. And this is the direction. So you have, this is called the pitch rate. Q is letter. And here, what is this is called? Yaw rate, which is given by R. So apart from 3 translation and these 3 rotational effects about this individual axis constitute the 6 degrees of freedom. And to understand this effect of this 6 degrees of freedom, the rotational effect of your body along with this translational thing, you require this body fixed coordinate system, because a vector attached to this, a velocity vector or an acceleration vector or a force vector or a moment vector, that can be best described if we have a body coordinate system, right? That's why you have to take that as well. So you know now what is body fixed coordinate system. This is non-inertial frame of reference. So body coordinate system is a non-inertial frame of reference. Why? Because aircraft is accelerating. Aircraft can have a rotational, local rotation with respect to body coordinate system. So it is non-inertial reference frame. So the absolute motion parameters, the variation of velocity, absolute acceleration, or absolute change in position or position change, all to do, you require inertial frame of reference. So these 2 coordinates are essential to account the dynamics quantities of a moving aircraft or flying car of a near future. Right. So we are going to look at what are those 6 degrees of freedom. So there are 6 governing equations, 3 force equation, and 3 moment equations. So there are 1 force and 1 moment equation, I can say, but that are resolved along XYZ direction. So there are 3 forces in XYZ direction, and there are 3 moments in X-axis, Y-axis, and Z-axis respectively. And that governs the entire motion of your aircraft to have it stable motion or to have a threshold values when that can go to unstable state and so on to do its an entire dynamics. So we are going to get that equations. That's what is called a Newton-Euler equation. So Newton equation are 3 forces components, and Euler equation are 3 moment equations for a rigid body motion in space, where we require to take a help of inertial frame of reference and body fixed coordinate system reference. So we were very much acquainted and solved problem with the inertial frame of reference without much of the time accounting body fixed coordinate system. But now we need to take the call of that as to do our vehicle dynamics study. And though we are going to derive today's class as 6 equations, which are a general framework for you, and the crux are the parameters, motion parameters involved in that, you'll understand. But we'll see that how those 6 equations become nicely decomposed, nicely reduced to have a simple 2 equations or 3 equations for our handling study of a passenger car. So that's what is the purpose of today's class, right? So let me just go ahead explaining you. So what is that I'm going to do now is I'm going to explain 2 important kinematic parameters. One is the velocity vector, another one is the angular velocity vector of this aircraft with reference to which are acting at body coordinates system, right there. So what are the two equations? One is its velocity vector. So the velocity vector would be having three components. I'll have ui plus vj plus wk. So this is where u, v, j, or u is the forward velocity, v is the lateral velocity, w is the velocity of ascent or descent coming down, right? So that are the three components, and this composition is what is the velocity of your aircraft CG. And this, let us say, this is equation number 1. And another equation is omega, rotational velocity of your aircraft with respect to 3 axes here, and that would be given by this roll rate component, pitch component, and your yaw rate component. So that's pi qj plus rk. So this is my equation 2. So these are the two motion parameters here. And I have to get now my forces and moment. So what is the objective of this complete derivation? Looking at it is to get a net force and net moment needed or acting in this vehicle to have its dynamics, right? So you see it's convenient to represent your velocity and angular velocity in a vector form, column vector form. You'll see that. So this is format of column vector form. Instead of writing that, I would write this as u, v, w. This is all for convenience of today's derivation. And this is the equation 3. And you would say immediately, I can represent my angular velocity by this column vector P, Q, R. So when I have that either 1 represent 3 or 2 represent 4, you should say. So now let's go ahead with the finding out this net force. So what I mean by net force is this value of the force. It will be given by force vector. That's going to be Fxi plus Fyj plus Fzk. This is equation 5. And my moment vector, that's going to be Mxi plus.
Sir,
Yes.
what is the symbol above F?
That's vector form.
Vector. Oh,
That's
vector.
you could have done it in school, and your school textbook would have an arrow like that.
Yes.
You see in any advanced textbook, an engineering textbook, you open, or literature you open, you don't see any more this kind of arrows, right? You will see a fiddle over that. So don't get worried about it, right? So I do sometimes writing it like that because still my habit of learning in the school days has not gone. I was trying to adopt always with the textbook notation. So the fiddle above this or this is all referring to vector. So whenever I represent in the form of a matrix like this, a column vector, I go for this. Whenever I explicitly show with an ijk, I will go with this. Right? Maybe I could, if that is so, I can put it like that. Right? Okay.
Yes, sir. Fine.
Are you comfortable? Yeah. So this is my equation 6. So similar way, you can say my f is equal to fx, fy, fz column vector. So this is 3 by 1 vector, and moment can be mx, my, mz. That's 3 by 1 vector, right? So this is what I have to get. So how do I get this? And these components, where are they located? They are located in body fixed coordinate system. So at the CG location of my aircraft, these force components, and with respect to the axis, it's CG location, these moment equations are going to take the governing of my vehicle motion in space. So how are they obtained? That's coming from our basic fundamental of understanding momentum. So to get your force, differentiate your linear momentum with respect to time. To get your moment, you differentiate your angular momentum with respect to time, right? So we are going to take that basic dynamic fundamentals, and we are going to derive this now. So what are those? So one is that if I know linear momentum, and that is P. So this capital P, I use it for linear momentum. Vector again is given by m into velocity, where m is a scalar quantity here. So this is equation 7. So if I differentiate this equation with respect to time, I would be able to get my force. But you see now the differentiation of velocity vector, where is this velocity vector? It's sitting in body fixed coordinate system, where that coordinate system is non-inertial frame, which is accelerating and having rotational effect of the axis of the vehicle body. So it is not simply only dv by dt. So that's going to be involved differentiation, and that we are going to see. So when I do find the rate of change of this linear momentum, I'll get my force vector. And similarly, what is my moment vector? I'll get it by angular momentum. So angular momentum, that's generally represented by HC. Again, it is by a column vector I represent. So I put this notation. This is again going to be 3 by 1. So I'll have 3 elements like that. So that's going to be given by IC, which is 3 by 3 into omega. So not omega, into omega. It's the momentum, right? Into momentum. So this is my eighth equation. So angular momentum is defined as so if I have here, this is a vector, this is going to be 3 by 1. So 3 by 3 multiplied by 3 by 1 will be 3 by 1. So this is the column vector. So angular momentum is a vector and linear momentum is a vector. But the important difference here is the linear momentum is having a proportionality constant, which is a scalar quantity, that's mass of your vehicle, whereas angular momentum depends upon a quantity, a matrix. It's not a single scalar value, it's called a tensor because it has got many elements in this 3 by 3. 9 elements are there, and that is what is called the centroidal inertia matrix. Centroidal inertia matrix. So you have studied in your rigid body mechanics in module 4, the centroidal inertia matrix as mass moment of inertia and product of inertia. So you are more focused on an area properties studied, and you had studied small part as mass moment of inertia and so on. So you should understand it is a property of your vehicle. It is not a vector or something. It is a matrix form because it has got many elements. And the property of your body during rotation would have many factors. So what is this IC? So how does it look like? So this IC is your centroidal inertia matrix, and that is going to be given by this IXX, IYY, IZZ, the diagonal terms, and off diagonal terms IXY, and here IYZ, IYX, and IXZ, and here IZX, and here IYZ, and here IZY. So there are 9 elements here, and if you look at IXY and IYX are equal for a symmetry structure of a rigid body. If a rigid body is an arbitrary body like some rock, which is that motion we look at in out of space, where this is not applicable there. You bring it there, and the rock is of irregular shape. There is no symmetry, and that is flying in space. And that you look at, and you have all these 9 elements. These all will be different. But if you look at any aircraft, so it is symmetry about its XZ plane. So when it is symmetry about XZ plane, this IXY and IYX will be same, IZX and IZX the same. So there are 6 independent quantities and 3 diagonal quantities and 3 off diagonal quantities. The 3 diagonal quantities are called the mass moment of inertia, and 3 off diagonal quantities are called the product of inertia. So for the benefit of you, how did you define this? Is for a 3-dimensional object, IXX would be defined as an integral of y squared plus z squared into dm. If it is ixx, it is this iyy, it is x squared plus z squared into dm and so on. How do I define product of inertia? Ixy would be minus integral xy product of coordinate into dm. So this is how you see the definition mathematically for these elements present in this centroidal inertia matrix, and that is primarily dictating relating to the angular velocity of rotation of your body with respect to body fixed coordinate system, and that gives you the value of angular momentum. And if you look at the change of angular momentum with respect to time, the rate of change of angular momentum, you would be able to get your moment equation. So if we have understood this fundamental, we're going to do now just a procedure. Maybe we are going to write, enjoy writing equations one after the other, and to see finally what are those 6 equations. And that's the end of today's lecture. And that would be comfortably finished in another 5 to 10 minutes within our time of the period, right? Hope you're enjoying along with me, writing down as I do enjoy. So now my basic properties is what, just whatever that I have told I'm going to do. Let me number the equation for convenience. So the equation of this IC, let us call 9 equation number, and these 2 sets are called equation 10. And then my 11th equation now is going with the basic dynamic principles from basic dynamic principles. So what do you mean by basic dynamic principles? Kinetics, the cause of motion to see, which causes this dynamics, the force and moments. So that is force vector, and that would be dp by dt. And that's going to be mass times acceleration vector, right? Yeah. So please, any doubt? And moment vector would be dhc by dt, and that's going to be ic times angular acceleration alpha. That's my equation 12. But now what is important is this acceleration here and this angular acceleration here in this equation 11 and 12 is not simple like what we think, simply dv by dt. And A would be equal to dv by dt only if I make a particle ideology. When I consider my body fixed coordinate system is not there, I look at my vehicle without considering entire shape, the physical geometry, then it is E is equal to dv by dt. Alpha is equal to d omega by dt, you can say. But it is not so now. Now you are looking at the velocities and the acceleration, the velocity and an angular velocity, which is in a body fixed coordinate system, which is non-inertial frame of reference, being from an inertial frame of reference. So your differentiation, the acceleration in the alpha would be bit involved in that. So for that to understand, let me just give, because that's going to be more number of terms to come. For convenient, we'll take a generic vector A, which can be a velocity vector, acceleration, force vector, anything which is in a body fixed coordinate system. How do we differentiate that with respect to inertial frame of reference is what we will just write, and that as a template we will develop the equation. So considering the general kinematic consideration, let me define an arbitrary vector A, which is AXI small I, see, that's body fixed coordinate system. It's there. AYJ plus AZK is the vector in body fixed coordinate system. If that is so, what is my dA by dt? So if I do that, what is my dV by dt? What is my dF by dt? What is my d anything? No, I can write it in the similar fashion. So the dV by dt is going to have 2 terms now. One is dou A by dou t relative plus omega cross A. Omega cross A. So you may ask, what are these 2 terms? So the derivative of A vector, which is in the body fixed coordinate system, which is accelerating as well as rotating in space, then if I have to get its absolute variation as function of time, then that would be given by the summation of these two terms. So first term would take care of the variation as an observer in the moving frame would think the change in the vector would be. So what is that? So this term is what an observer in the moving frame. For example, a pilot of the aircraft would think the change in the vector A would be. So this is what does this mean? And what is this term? This term would take care of the rotational effect of your body fixed coordinate system, and that influence on this vector. So that's given by this cross product, and that would be obtained through a determinant. What is that? It is going to be I, J, K, and here omega, that's going to be P, Q, R. You know, P is roll rate, Q is pitch rate, and R is yaw rate. And A vector components AX, AY, and AZ. So this determinant would give you this. So addition of these two would give me my absolute variation of this vector A. So what is this quantity? So dou A by dou T is its time derivative in that coordinate. That would be simply its time derivative AX dot AY dot and AZ dot. So what is now my yeah.
Then dou A by dou T, what is the subset?
Relative,
Oh, okay.
REL. Relative. The variation of A relative to body fixed coordinate system. If you know that and then account the rotation motion of your body fixed coordinate system together, then you would get an absolute variation of this vector A. So if this happens to be replaced by velocity, then I get my acceleration vector. So mass times this acceleration vector would give me my force vector. Are you getting my point? Right. So now let's continue numbering so that we'll keep track of what we are doing nicely. So this is equation 12, and let me call this is equation 13.
Excuse me, sir.
Yeah.
So can you explain the top equation once more? I didn't understand that part.
What is that once again?
Can you explain the one equation on the top?
This one.
So, no, scroll a little more up, sir.
Yeah.
Yes, sir. That from basic dynamic principle, right? That from there onwards, I didn't understand the
basic dynamic principle. Yeah, this is fundamental. So again, okay, I understand. So this is simple. You have done your engineering mechanics course, right? That's a prerequisite for that. I'll just get to your point. I understand what is the difficulty that we have. So this is equation 14 and this is equation 15. Let's go ahead writing equation 16. Before that, I'll clear your doubts, so that you would comfortably follow the rest. So, you know, what is the definition of force? That's from Newton's second law. What is the Newton's second law? Force is equal to mass times acceleration, or the rate of change of linear momentum, you are saying, right? So that's the Newton equation, Newton's second law. First equation is clear for you. Is that correct? I do not know who was asked.
Yes, sir. That's right, sir.
Your name, please?
Sir, Roshan, sir.
Huh?
Roshan.
Roshan, yes, Roshan. Because I'm not able to see my students on the screen. I see my board only.
Yes.
And Roshan, this second equation is the moment equation. You know the effect of moment. So you have studied in your rigid body mechanics. The moment you come out of your particle ideology and you are looking at your any rigid body with the physical geometry, the force acting on it can make an effect in a body called rotation, right? You could have studied a door hinged on the wall. When it is being pushed by a force, it is not translating out of the wall. It is rotating about the hinge point, right?
Yes, sir.
Yeah, the rotation is caused by what?
The force applied. on
Force
the hinge.
applied. And that force in turn, what is it pursued in the door as a moment?
Moment. Yes.
That is r cross F vectorial, right? And that moment is what is now the moment vector, which makes the rotation of your body aircraft to roll about its longitudinal axis or pitch about its lateral axis or to take a navigation, take a turn in sky. No, yaw motion, the change in orientation of your aircraft in the top view, that motion, and that are responsible by mx, my, ms. Are you getting my point?
Yes, sir. Understood, sir. Thank you.
So when I require only the first equation, when I make my study of an aircraft motion, I'm interested only looking at what is the trajectory that aircraft flying. Sometime in the morning in the sky, we see fog line left and then there is a jet going up. So we look at only the trajectory. If we are interested is only the trajectory, you can treat your aircraft as a tiny appearance of that aircraft in the sky. At that time, do not look at the physical geometry. So the first equation, 11 alone sufficient to describe its translatory motion in a space. But the moment I go more in details of the study of its rotational aspects, that diving action of your aircraft or roll action of your aircraft or change in orientation of your aircraft, I require the physical geometry. The moment I look at the physical geometry, the force that are developed through the engine in the aircraft would manifest like a force on the door manifesting the moment, a moment on a aircraft at its CG location. And that is what is mx, my, ms. How do you get that? That would be analogous the way you get your force, the way you get your rate of change of angular momentum. So that is called an Euler equation. So the second equation is what is called the Euler equation. That's why these two together called Newton-Euler equation for rigid body motion. And this is defined as the rate of change of angular momentum. Is it clear to you?
Yes, sir. Yes, sir.
Yeah.
Thank
So
you.
continuing with this definition of an absolute quantity derivative of vector A, I require these two terms to be added together. That's the equation 14 plus equation 15 answers together. I'll get it. So that's my equation 16. So what is my equation 16? I'm going to write it like that, and that is the template for me to further write the equation quickly. And that is dA by dt, and that's going to be now this term first. See, this dA by dt is what is again 3 by 1 vector. So first element is ax dot plus the element from this determinant. The element from this determinant. So what is this element from this determinant? It's I into azq minus ayr minus j into az p minus axr plus k into ay p minus axq, right? So these are the elements. So the first element should be added with this. So first element when I add here, that's going to be azq minus ayr.
So my next class has started, can I leave, right?
Yeah, you can go, and later on you can watch the rest of that. I have always told that, right?
Thank you, sir.
Because this is I'll have to finish it so that it will be wholesome. And then that ay dot plus az b minus axr and az dot plus ayp ayp. Here I would change this minus sign stuff, I put plus. So this is axr into azp. Let me put it like that. So that the minus sign here is taken as plus, and this is, and then az dot plus ayp minus a subscript x q. So these are my derivatives. And if I put here velocity, I'll get my acceleration. Then mass times that would be my force equation. Similarly, I'll have to write for derivative of my angular momentum. then I'll have another 3 equation. So this is simple procedural. I will be just doing it in another 2-3 minutes, and that would be end of the lecture. If you are to go for the next lecture, you can proceed, and later on again listen to this. So this is equation number 16, and let's now look at how do I get now for this. So now it's just simple, straightforward. So dp by dt is what is my m dv by dt, and that's going to be now m into dou v by dou t relative term plus omega into velocity vector upon the rotational effect of a body. And that's going to give me now force vector. I'll write it now in a column format so that you'll have the respective equation fx, fy, fz readily. That's going to be fx, fy, fz, 3 components of this force vector at CG location of the body, and that would be mass times. Now, what is the first vector? V vector. Derivative of v vector. So derivative of v vector is what? It's vx, that is u dot, v dot, and w dot, and plus terms are there. What are the additional terms? Here it is qw minus rv. Where if you look at here, w refer to what now? Your az, and this is referred to ay. So the equation what we had, you can just replace ax, ay, az accordingly in equation 16, and that's your equation here. So this plus ru minus p small p w plus pv minus qu. So these are my 3 force equations. So equation 17, and this is called a Newton equation for translation of a vehicle. So accounting for 3 degrees of freedom of a space vehicle out of 6, and then other 3 rotational degrees of freedom can be obtained similarly. That is m vector would be d of hc by dt. That's going to be dou hc by dou t relative term plus omega cross hc. Why do I put the fidelity here? I will write as a column vector 3 by 1, and this is going to be 3 by 3. Right? That's essentially 3 by 1 again. So this, and that's going to be like this. So let me just write down here. I will have what is my hc? My hc is now column format. It is horizontal hx, hy, hz. So angular momentum with respect to x-axis, y-axis, or axis respectively, that would be IC, the centroidal inertia matrix 3 by 3 times omega. That's 3 by 1. That's going to be now. So this is, you know, Ix, Iy, Z, the components, 9 components. So this product, this is 3 by 3. So this is going to be 3 by 1. So I'm writing this vector, which is my angular momentum vector. So what are those? That's going to be Ixx p plus Ixy q plus Ixz r. Yx p plus Iyy q plus Iyz r. Izx p plus Izy q plus Izz r. So this is what is angular momentum now, which is influenced by our inertial matrix, centroidal inertial matrix. And now it's straightforward. So this h dot, if I do, what is my m vector? That's going to be mx, my, mz. So 3 equations, and that are going to be like I have my a vector, a dot, ax dot, ay dot, az dot you have written, or u dot, v dot, w dot you have written. Now this term all would be there with the derivative because Ixs, Iyx all are constant quantities. It's not varying with respect to time. Whereas PQR are varying with respect to time. So I will have first term like U dot, V dot, W dot in force equation. Here I'll have Ixx P dot plus Ixy Q dot plus Izx Ixz R dot. Right? And similarly, I can write this Iyx P dot plus Iyy Q dot plus Yz R dot, Izx P dot plus Izy Q dot plus Izz R dot. So this is first term. That's it's the dou Hc by this term. Now this determinant would be what? This would be determinant by I, J, K, and you will have here this omega would be PQR, and Hc would be Hc is this. So this first term is this over here. Second term here, third term here. So this determinant would get added, and that would be a lengthy equation. That's all. We should not worry about it remembering and all. We need to know this, and we are not going to solve such a big equation in our dynamic study. But it will be easier that you work in future in aircraft dynamic engineer, and you have to do coding, or you have to do for a generic vehicle motion, or you are working in today's startup hybrid vehicle, flying car, and tomorrow you are working in space study and so on. You are requiring the coding. Then that fundamentals of Newton-Euler equation. These equations are required to be converted into codes. So for that purpose, you have to write down and enjoy doing this process, right? So I just to finish this, and that's the end of the lecture. And so here, what is the term is going to be I into Q this minus this. So that term is what I'm writing here. So Q into Ix, that's going to be W. That's going to be the third term. So it is going to be Izxp plus Izyq plus Izr minus Q into this minus R into this. So R into this term is what? The second term. So Iyxp plus Iyyq plus Iyzr. So that's all. So my first equation is what? Mx is equal to this. That's my moment equation. Similarly, I'll get the My. That's for pitch motion. I'll get for yaw motion. So you can easily write this here. So what is the second equation? So the second equation, when I have to write, that's going to be now R into. That's R into, right? So in the determinant, when I do, I have written here this. So My when I do this equation plus here. So the second term of that would be what? Minus J into this minus this. So I will write plus. So I would reverse this R into this term and P into this term. So that's going to be R into first term is what? This Ixx P plus Ixy Q plus Xz R minus P into, you understand how do I write P? P into this term, third term. The third term is here. So Izx P plus Izy Q plus Izz R. This is my moment about lateral axis. And similarly, moment about Z axis, that K into this. So P into this and minus Q into this. So that's P into this term, that is, what is that? Is the second term, right? That is Iyx P plus Iyy Q plus Iyz R minus Q into first term. So IXXP plus I Y X IY IXYP IY IXYQ plus IXZR. So this is what are the three terms. So here again, this is column vector, right? So this is all one term, one element. If I substitute and get a numerical value. So this is 3 by 1 matrix. So this is your 3 by 1 column vector. So I get my moment equation. So there are three moment equation. Let me number this now. What was that equation earlier? 17. And let's call this as 18. So this equation 17 and 18 are called Newton-Euler equation for a vehicle in space for its 6 degrees of freedom motion. So this equation is Newton-Euler equation for 6 DOF of vehicle in space for its 3D motion. But what does that we needed? What we needed is for ground vehicle for a passenger car. So the equations out of the 6 are not required all as a whole, and that's very simplified form. And those equations are the fundamental equation for our lateral dynamic study. With that, I'm going to start in the next class. So I stop at this point of time. I'm sure that you have understood, you have appreciated, enjoyed this particular lecture. Though it is a bit of advanced thing appearing along equations, you should not worry about it. You're just doing your engineering. You've got a long way to go ahead, and you should see this all as a generally accepting way, right? So all the very best, and let's meet again on this Monday morning, A1 slot at 8 o'clock, and start with our bicycle model for our vehicle handling study, and understand how nicely this equation 17 and 18 Newton-Euler equation can be reduced to the requirement of vehicle handling on a ground for a passenger car. That's a starting point for the next class, and I would end the lecture at this point of time. Stop recording.